Hello and welcome back. We're going to start section 5, which is something called symmetry. And I want to think of it's kind of like, um, it's kind of like a reflection. But symmetry, I like to think of like a butterfly. Okay, a butterfly. And do you guys know that butterfly? There is no other word in the English language that rhymes with butterfly. Okay, let me just put an image here of the butterfly on the page. And the reason why I put this image of a butterfly is because the left side is the same as the right side. So if I were to like cut this in half, then what happens is that the butterfly mirrors itself, okay, over a line of symmetry. It mirrors itself over a line of symmetry. Okay, and so what we want to do in this one is we want to identify reflectional symmetry in geometric figures and the number of lines of symmetry. We want to identify rotational symmetry and its order in geometric figures. So the first thing we have is reflectional symmetry. Okay, and so of a geometric figure is the characteristic of a figure to map onto itself across a line of symmetry. So if I were to look here and identify where this has a line of symmetry, and basically, let's write this. Reflectional symmetry means, and here's how I like to put it. Okay, I like to ask the question, where would you fold on an image to have it fold onto itself? Okay. That's another way of putting it. Okay, so if I were to like fold this in half and get it to go onto itself, then what I would do is I would try and fold it along this line. Okay, and this line is called my line of symmetry. Okay, and then, all right, so what you might have is reflectional symmetry of a geometric figure is the characteristic of the figure to map onto itself of a line of symmetry. Now notice what happens here is that we have developed two different lines of symmetry for that same problem. And what I notice is that there's only one line of symmetry that would fold onto itself. Okay, in these other examples, you have these other lines of symmetry that wouldn't fold it onto itself. Okay. All right, let's take a look at the next one. Okay, so the number of lines of reflectional symmetry will vary for each geometrical figure. Okay, the figure is said to have n-fold reflectional symmetry. N is the number of lines of symmetry. Okay, criteria for lines of symmetry when crossing from an angle to an angle. It is an angle bisector of both angles. When crossing from a vertex to a side, it is an angle bisector of the vertex, and it is a perpendicular bisector to the side of the figure. When crossing from side to side, it is perpendicular bisector of both sides. Okay, so when we do this, really when I draw in this line of symmetry here, what I'm doing is I'm bisecting this angle here. Okay, this angle is bisected. This segment over here, these two segments are bisected, and this is going to create a right angle at that point. Okay, so then, all right, let's take a look. It says, what is reflectional symmetry for trapezoids? Okay, so what I want to look at is where do I have symmetry in this figure? And in this figure, I only have one line of symmetry, and that's going to be straight down the middle here. Okay, what that's going to do is create two congruent parts here, two congruent parts here, and it's going to form a right angle on that one. Okay, over here for this one has no line of symmetry. Okay, some figures just aren't symmetric. Okay, and that's that. Okay, now what else is cool is that regular polygons with n sides, regular polygons mean figures with the congruent sides and congruent angles have n-fold reflectional symmetry, and I want to talk about that. So because this triangle is a regular triangle, this has 3 congruent sides, okay, 3 congruent sides and angles, okay, we're going to have 3 lines of reflection. 3 lines of reflection. And so if I drew one of these lines of reflection, it would go like this, okay? The other one would look like this, and the third one would look like this, and there aren't any others, okay? And that's that, all right? On all of those, you could fold those over, and you would get, you know, the same piece of paper. All right, now on this one, okay, this is a hexagon. Now, I've got an issue with this because I can draw in 1, okay, so a hexagon has 6 sides, so we should have 6, you know, lines of symmetry. Okay, here's 1. Oh, no, we do. Never mind. 1, 2, all right, 3, okay, 4, okay, I can fold it along the corners as well, 5, and 6. Okay, so this is a hexagon, okay, which means it has 6 sides, okay, which then leads us to the idea that we have 6 lines of symmetry. Okay, and that's it. All right, this one says in each diagram represents a line of symmetry, or which diagram represents a line of symmetry for the regular polygon. And so that one would look like this, okay, where you get a bisected angle up here, you get 2 congruent parts down here, and you get right angles from the other side. Okay, so that's what that's got. All right, let's look at the next page. Okay, so we want to analyze the reflectional symmetry of these regular polygons, okay? And so because a square has 4 congruent sides, we're going to have 4 lines of symmetry, okay? And so a square has 4-fold reflectional symmetry. Okay, an octagon, now this would be a lot of work to do, but because I know an octagon has 8 sides, that means that we're going to have 8-fold reflectional symmetry. So you're going to have 8 lines, all right? And I'm not going to do that or go through that. I'm just going to move on, okay? Now let's talk about rotational symmetry. Okay, rotational symmetry of a geometric figure is the characteristic of a figure to map onto itself through the center of rotation. So the center of rotation is always here. Okay, the number of rotations that map the geometric figure onto itself is called the order of symmetry. Okay, and so here's what I've got. You know, so if I were to take a figure like this, and let me go back to my face. Okay, and if I were to take my face and rotate this about the center, okay, then the question is, let me slow this down too. All right, at what point, you know, what's my rotation have to be until my face is back onto itself? So in this one, I have a rotational symmetry of 1 revolution, which is 360-degree rotational symmetry. Okay? And so we're trying to figure out how many degrees do you have to rotate something to get it back onto itself. Okay, now if I were to take something like, say, a Chipotle burrito, okay, and if I were to rotate the Chipotle burrito around, at what point does that map back onto itself, okay? And I know a Chipotle burrito isn't exactly congruent, but this has 180-degree rotational symmetry, okay? So every time it goes a half turn, you're kind of back at where you started, okay? So if you start here, all right, at 180 degrees, you're going to be back to where you started. So this is 180-degree rotational symmetry. Okay. Now let's go here and look back over here. All right, and take a look at this. you know, a lot of these will have, you know, like this hexagon here would have, I think, 30-degree rotational symmetry. But if you rotate it 90 degrees, you're not going to get the same thing. But if you rotate it 180 degrees, you'll get the same thing. All right. Same thing with like a you know, with a like a rectangle. Okay, if you were to rotate this rectangle, you know, it wouldn't be it wouldn't it you know it would a 45-degree rotation wouldn't get you back to where you were originally to have that same shape. So this one would require a 180-degree rotation to get back to itself. Okay, so the rectangle has rotational symmetry of order. Okay, so for this one, the rectangle has rotational symmetry of order, and we're going to call this of order 2. Okay, so that what happens is if I rotate this around, okay, okay, and I'm going to do that like so down here. You know, what I notice is that, you know, when it's right side up, okay, it would look like that, all right? And so that's a 180-degree turn. And if I rotate it a full 360, we get back to where we started, okay? So this is only happening, you know, when I rotate this, I get this back when I do 180 degrees or 360 degrees. That's what gives me an order of 2, okay? And this would occur at 180 degrees and 360 degrees, okay? And that's when that's going to occur. So if we were to go to the next page and talk about what is the order of rotational symmetry for the two trapezoids, you know, because, you know, if I were to rotate this around to get it mathed back onto itself, this would have an order of 1, okay? And same thing over here, okay? This one would also have an order of 1 because I would have to rotate each of these 360 degrees to get her back to our original, okay? Okay, so then we can also talk about, you know, something like a hexagon. So a hexagon, for regular polygons, the order of rotational symmetry is equal to the number of sides n, okay? And so what I know is that, you know, for this, we would do, because this is a hexagon, okay, it has an order of 6 for rotational symmetry. Okay, and if I wanted to find the angle that this would give me, this theta, what I would do is I would take 360 degrees and divide that by the number of sides in this case, which is 6, and that would give me a value of 60 degrees for my smallest angle of rotational symmetry. So I could rotate this thing 6 times 60 degrees, and it would bring me back to where I started. Okay? Okay. Consider the regular dodecagon. Now remember, a dodecagon has 12 sides. Okay, this has 12 sides. Okay, which statements are true regarding the regular dodecagon? Okay, so the smallest angle of rotational symmetry for the dodecagon is 30 degrees. Well, let's check. What's 360 divided by 12? And that would end up giving us 30 degrees. So this part is true. Okay, the dodecagon has a rotational symmetry of 180 degrees, and this is true, it does, okay? So I could rotate that 180 degrees and it would give me the same thing, mainly because I have an even number of sides, okay? The order of rotational symmetry for the dodecagon is 12, and this is false, okay? Or I'm sorry, 10. It should be 12, okay? The dodecagon has rotational symmetry of 135. Well, 30 is not a multiple of 135. Okay, so this is going to be false. Okay, so the angles of rotational symmetry for the dodecagon are multiples of 30, and that would be true. Okay, and that's how I'd want to go through that. All right, on this we want to determine the reflectional and rotational symmetry for the regular pentagon. So because this is regular, all these sides are congruent, okay? And so the reflectional symmetry, you know, I would have the following. Let me do this in blue. And so I would have, or I'm sorry, red. So here'd be one line of reflection. Here's the other 3, 4, and 5. Okay, so this has 5 lines of reflectional symmetry. Okay, and rotational symmetry means that this is order 5, and my smallest angle would be 360 divided by 5, which is going to give us 72. Okay, so 72 degrees would be my smallest angle. Okay, let's look at the last one. Okay, a decagon, which has 10 sides, okay, has 10-fold reflectional symmetry. The order of rotational symmetry for the decagon is going to be 10. And the smallest angle of rotation is going to be 360 divided by 10, which is going to give us 36 degrees. Okay, so pretty, relatively simple stuff. Can be confusing at times. I hope you guys enjoyed this video, and we're all set to finish this unit. And so work on Edgenuity, and then make sure you take the unit test, or cumulative test, rather. See you, bye.